Welcome to G Fun Facts Online. In the race to build the ultimate computer, we often think of light-speed processors and complex superconducting circuits. But what if the key to unlocking the next computational revolution isn't about going faster, but about listening closer? What if the future is being built not with photons or electrons, but with the most fundamental form of mechanical energy we know, sound? Today, we're diving into the strange and fascinating world of phononic quantum computing, where scientists are learning to store the most delicate information in the universe inside a single, quantized particle of sound. This isn't science fiction. It's a quiet revolution happening in labs right now, promising to solve some of the biggest problems in quantum physics and build a new kind of computer, one vibration at a time. To understand why sound is becoming so important, we first need to understand the problem it's trying to solve. At the heart of any quantum computer is the qubit. Unlike a classical computer bit, which is either a 0 or a 1, a qubit is a master of uncertainty. Thanks to a property called superposition, it can be a 0, a 1, or both at the same time. Now, link multiple qubits together, and you get another bizarre quantum trick: entanglement. This means the state of one qubit is instantly connected to the state of another, no matter how far apart they are. It's this combination of superposition and entanglement that gives quantum computers their almost mythical power, allowing them to perform millions of calculations simultaneously. But here's the catch, and it's a big one. These quantum states are incredibly fragile. They're like a soap bubble on a windy day. The slightest disturbance, a tiny change in temperature, a stray electromagnetic field, even a physical vibration, can pop the bubble. This process is called decoherence, and it's the arch nemesis of quantum computing. It erases the quantum information, turning your powerful qubit back into a boring old classical bit. For decades, the biggest challenge has been finding a way to protect qubits from this environmental noise long enough to do something useful with them. And this is where sound enters the picture. Or, to be more precise, the phonon. In the world of quantum mechanics, just as light is made of particles called photons, sound traveling through a crystal is made of quantized packets of vibrational energy called phonons. You can think of a phonon as a single, indivisible particle of sound, a tiny ripple of energy moving through a material's atomic structure. Scientists began to wonder, what if we could use these phonons as a storage locker for our fragile qubits? Mechanical vibrations, like sound, are naturally isolated from the electromagnetic noise that so easily disrupts other types of qubits. By converting the quantum information from an electrical state into a mechanical vibration, we could potentially shield it, giving it a much longer lifespan. It's like taking a precious, fragile document, and instead of leaving it out in the open, sealing it inside a secure, soundproof vault. The vault, in this case, is a phonon. So how exactly do you imprint the information from a qubit onto a particle of sound? The magic ingredient is a phenomenon called piezoelectricity. You've probably encountered this without realizing it. It's the principle that makes a gas grill lighter spark when you click it. Certain materials, when you squeeze them, generate an electric voltage, and conversely, if you apply an electric voltage to them, they change their shape. They vibrate. This two-way street between electricity and mechanical motion is the perfect bridge for our quantum information. In a typical experiment, scientists start with a standard superconducting qubit, which operates using microwave signals. They then couple this qubit to a tiny sliver of piezoelectric material that acts as a mechanical resonator. By applying a precisely tuned microwave pulse, the electrical energy of the qubit, its unique state of superposition, is converted into a mechanical vibration in the resonator. A phonon is created, and it now carries the exact quantum state of the qubit. To get the information back, you just reverse the process. The phonon's vibration is converted back into an electrical signal, which the superconducting circuit can read. It's a stunningly elegant act of translation between two different physical worlds. Researchers are exploring two main ways to build these sound-based systems. The first is called surface acoustic waves, or SOWs. Imagine a tiny earthquake tremor traveling along the surface of a microchip. These SO devices can be designed to create a moving pocket of energy that can trap and carry a single electron across the chip. The spin of that electron acts as the qubit. This flying qubit architecture, pioneered by Professor Andrew Cleland's team at the University of Chicago's Pritzker School of Molecular Engineering, is a way to physically move quantum information from one place to another. In a truly groundbreaking experiment, his lab created what they called an, quote, acoustic beam splitter. They were able to take a single phonon and put it into a superposition of being in two different places at once. This is a fundamental building block for a computer built entirely on mechanical principles. Their work has been so promising that the Department of Defense has invested millions to continue exploring the potential of these sound-based systems. The second major architecture uses something called bulk acoustic wave, or BAW resonators. Unlike SOWs, which travel on the surface, BAWs confine the sound waves within the entire volume or bulk of a material. Think of it like a bell ringing, where the vibration is happening throughout the metal. These BAW resonators can be engineered to vibrate at extremely high frequencies and, most importantly, for a very, very long time. This makes them perfect candidates for high-quality quantum memory. Researchers at Caltech and Yale University have been leading the charge here. The Sholkopf and Rakich labs at Yale showed they could successfully couple superconducting qubits to these BAW resonators, leading to a dramatic increase in how long the quantum information survived. Building on this, a team at Caltech, led by Professor Mohammad Mirhosseini, achieved a landmark result. By converting a qubit's information into a phonon inside one of these mechanical oscillators, they extended the storage time of the quantum state by a factor of 30 compared to keeping it in the original superconducting system. That's a huge leap. We're talking about extending the life of a qubit from less than a millisecond to over 25 milliseconds. That may not sound like a long time, but in the world of quantum computing, it's an eternity, enough time to perform thousands of complex operations. This brings us to the core advantages of this phononic approach. The first, as we've seen, is dramatically extended coherence times. By storing information in mechanical vibrations, qubits are naturally shielded from the stray electromagnetic fields that are a constant source of noise for other systems. They are simply less talkative with their environment, which allows them to hold on to their quantum secrets for much longer. The second big advantage is size and scalability. Here's a mind-bending fact. The speed of sound is about 100,000 times slower than the speed of light. This means that for a wave of the same frequency, the wavelength of a phonon is 100,000 times shorter than the wavelength of a photon. What does that mean for computing? It means the components you build to manipulate phonons can be incredibly tiny. This miniaturization is critical. One of the biggest hurdles to building a truly powerful quantum computer is the sheer physical space required. Photonic and superconducting systems can be bulky. Phononic devices, on the other hand, offer a path toward packing millions of qubits onto a single, compact chip, making the dream of a large-scale quantum computer much more achievable. The third, and perhaps most profound, advantage is that phonons can act as universal translators. Different quantum technologies operate best in different domains. Superconducting qubits are great for processing and operate at microwave frequencies. But for sending quantum information over long distances, you need to use light, or optical frequencies, that can travel through fiber optic cables. How do you bridge that gap? Phonons are the perfect intermediary. They can efficiently convert quantum information from the microwave domain of a superconducting processor into the optical domain for communication, and back again. This transducer capability is the key to creating a quantum internet, a global network that could connect quantum computers, enabling ultra-secure communication and distributed quantum computing on a massive scale. Now, as with any revolutionary technology, it's important to have a reality check. The field of phononic quantum computing is still young, and it faces some significant challenges. While phonons are great at ignoring external electromagnetic noise, they aren't perfectly immune to decoherence. They have their own sources of noise. Random thermal vibrations, essentially heat within the material, can disrupt the delicate quantum state. Tiny imperfections in the crystal structure of the material can also scatter the phonons, destroying the information they carry. This means these systems still need to be operated at extremely cold, near absolute zero temperatures. There is also the sheer difficulty of fabrication. The devices we're talking about are nanoscale. They have to be built with atomic-level precision to work correctly and consistently. This is a monumental engineering challenge. And while the small size is a plus for scalability, actually figuring out how to connect and control millions of these phononic qubits without them interfering with each other is a puzzle that researchers are still working to solve. Finally, how do you measure the state of a single phonon accurately without accidentally destroying the very information you're trying to read? Developing these precise measurement techniques is a major area of ongoing research. Despite these hurdles, the pace of progress is astonishing, driven by a global community of scientists. Beyond the pioneering work at Chicago, Caltech, and Yale, other top institutions are pushing the frontiers. At ETH Zurich in Switzerland, researchers are coupling acoustic resonators with superconducting circuits to explore new frontiers in quantum measurement. At UC Berkeley, the Quantum Devices Group is engineering new ways to make phonons and qubits interact, aiming to create even more robust quantum memories. And just recently, researchers at Rice University achieved an unprecedented level of control over the interference between phonons, a breakthrough that could lead to new types of quantum sensors. This global effort is pointing toward an exciting future. The most immediate application will likely be in creating those robust, long-lived quantum memories. These are essential components for any large-scale quantum computer, acting as a scratch pad to hold results from intermediate calculations. The next big step is quantum networking. Phononic transducers could become the backbone of the quantum internet. But perhaps the most intriguing applications are in sensing. The very sensitivity that makes phonons a challenge also makes them incredibly powerful sensors. A device built on phononic principles could potentially detect the gravitational field of a single bacterium, or identify the presence of a single rogue molecule, opening up entirely new possibilities in medicine and materials science. The journey to build a useful, fault-tolerant quantum computer is a marathon, not a sprint. For a long time, the race has been dominated by technologies based on light and superconductivity. But by turning to the fundamental world of sound, of physical vibration, scientists have uncovered a new and powerful pathway forward. Phononic quantum computing offers a compelling solution to the critical problems of decoherence, scalability, and connectivity. The challenges are real, but the symphony of breakthroughs from labs around the world suggests we are on the cusp of a new era. An era where the most complex calculations in the universe are performed not in a flash of light, but in a perfectly controlled, quantized vibration. The future of computing, it turns out, might not be silent. It has a new and very promising sound. Thanks for listening to G Fun Facts Online.